All right, so we're back. I've been away for a bit because I've been dealing with some internet problems, which has been fun. Let me just turn all this stuff off. Yeah, it turns out that somebody effectively hijacked my internet connection without meaning to, I think. So that was a bit of fun. So I was down for, I don't know, a couple of days. Anyway, so I'm back. And I've been working on my crypto in the meantime without internet. The beauty of programming is that you don't need an internet connection if you have your documentation. And I could use 4G on my mobile anyway. But I couldn't stream and I couldn't do anything really interesting on the internet. So, but what I've got here is now a working GCM implementation, which is pretty cool. Sorry, it's got some music going in the background here. I need to turn it down a bit. If I can find it. All right, so yeah, so what I've ended up doing is effectively, I mean, if you look at the other video that I put on YouTube, it's kind of embarrassing how wrong I got stuff. But what I've got here is an implementation that actually works. Where am I? Okay, cool. And so yeah, it's not the best code. It's not as clean as it could be, but it's okay. It definitely needs refactoring. Like, this is just me getting the algorithm working. And that's the thing with programming, right? Different people do things, approach it differently. I've always been a fan of approaching it in a pragmatic way as much as possible, without taking too much shortcuts, but just getting an end result, getting it correct, at least for a subset or a set of test cases. And so, you know, you saw me sort of doing, I wouldn't call it test-driven development, but I was writing unit tests to test the code that I was writing, which wasn't really test first, I guess. But I'm not really I'm not a TDD fan anyway, really. But I am a test fan for sure, a unit test fan. So anyway, and so what I've got here is an implementation that works. My test at the moment is just over a single use case or test case, so single key and initialization vector and ciphertext and all the other bits that you expect here. So this is the additional authenticated data. This is the tag we expect. That's the plain text we pass in. So the two things that we basically are checking for is that we get this ciphertext and then we get this computed tag. And all I have at the moment is a high-level function, which I'll eventually turn into a public method or a public function rather, in a module. And then that thing just passes key, IV, you know, the plain text, any additional data we want to pass in, and then we test. We compute the ciphertext and the tag, and I pass in tag length now, tag size, in bytes. So this is the number of bytes that we do expect the tag to be, and that'll effectively just get the most significant bytes in the computed tag. Anyway, and so this works. I don't need all this stuff. So if I run our little program here, cargo run, we get that. If I run the test, I see everything passing. Now, obviously I need to build this out. I need more than just one test, and I'll do that. I did have all these test vectors that I was using, and these are good. And I'll write a test harness to parse this and then run every single one of these tests, and that'll give us pretty good test coverage, and I'll be pretty confident that things work there once I pass all these tests. And I'm sure I have bugs, like I guarantee you, there's no doubt in my mind. Every bit of code everyone writes has bugs all the time, but hence tests. And so this works. All I've implemented is the authenticated encryption algorithm. I haven't done decryption yet, so that's something I'll work on today. If you look at the actual encryption algorithm, it's pretty messy. What it does at the moment is it builds a key schedule for AES, and I use my AES-128 implementation, pass in the key schedule, and I get this thing called a hash subkey, which is 128 bits. It's a block, basically. Then I build out the IV, the initialization vector. I have to pad that. So if it's not 120, what's 12 times 8? If it's not, this is where it gets embarrassing again. If it's not 96 bits long, then I do this padding. Otherwise, I just I build it out this way. And so you end up with this 128-bit block for the initialization vector as well. So, you know, if it's 96, then bit shift it 32 bits to the left and add in these 32 bits, which is 4 bytes, obviously. So that all works. And otherwise, we pad it. We use ghash. So we do a little bit more work. We sort of work out how many bits we need to pad it, and then we put in the size of the IV in bits, and we OR that together, I guess, at some point. We just push it. Oh no, that's right. So we actually end up. So this is just a single 128-bit block, right? But here where we end up with more than one, potentially. We end up with 2, and at least 2, and then we ghash it, and that gives us a single block back. Then we pass that into GCTR, and this thing does the encryption. So this is where we'll end up with ciphertext coming out, and so that's kind of the first step, if you like, of the encryption. We get the ciphertext. The next bit is quite involved. We have to build the tag, and you have to build that up based on, you know, basically you have, you know, the additional data. You have 0 or more 0 bits. You have the ciphertext, and you have 0 or more 0 bits again, then the length of the additional data, and then the length of the ciphertext, and you sort of put this in one big bit string, and then you pass that into, in this case, ghash again, with the hash subkey. That gives us a block back again, and then I pass it through GCTR again with I think it was the initialization vector there, and the result of ghash, and you get a tag, and then depending on the tag size, you basically pull out the most significant bytes of that or bits of that. So this all works. It's messy as hell, and I need to improve this. This is kind of the encryption part, and so this is a bit nicer. But again, like all my interfaces are really naive. It's just byte interfaces everywhere, or maybe 128-bit block interfaces. Like it needs to. I need to really think about refactoring this code. There's no high-level abstractions here. I mean, it's not nice code in that sense. Not well designed from a software engineering point of view, but it works for now. And then, so anyway, you can sort of see what's going on here. We have a counter block, and then we compute that. We pass it in, but we keep computing that using the increment 32-bit inc32 that we created earlier. I'm not sure if I created that on stream last time. Anyway, and then we loop through 128-bit blocks, these 16-byte blocks, and we end up with. If it's a partial block, then we handle it especially. If it's a full block, then we do this. And basically, what you're doing is extending. I'm basically building this byte array, or this vector, bytes, and that's what we end up outputting, which is the ciphertext. So that's it's pretty straightforward. Yep, and then ghash is pretty easy. So I'm not doing any error handling as well. I've got runtime asserts in here that need to be changed to proper error handling, or not even error handling, just actually handling each case properly. So here we just use the mole blocks method over every block. So we sort of loop over every 128-bit block, and we just effectively just incrementally call mole blocks over the previous result and exclusive OR it with the bit string, which is or the block rather. So that's pretty straightforward. It turns out that molblocks was wrong completely, so that was pretty hilarious. First thing that was wrong was that I was treating the endianness incorrectly. So bit strings, according to the spec, if you look at the spec, bit strings are little endian, and so I'm just sort of doing that by reversing the way that I iterate over the bits, and then I had the actual implementation really wrong. My implementation was so complicated. I'd misinterpreted the spec. But anyway, I cleaned that up. I mean, I could still clean this up further, but this is actually, as far as I know, correct. And then it returns the result as a 128-bit block. The inc32 function I built myself. Obviously, it's probably not optimal, but it works. And you do this modulo 2 to the power of 32. So I'm using wrapping add here, which is a nice function that Rust gives you for the primitive types. So U32 has a wrapping add, which is nice, and so I could just call that, and that should be efficient. And then I pull that together. I do use MSB. It works on bytes now. I think originally I had it on 128-bit blocks, so I changed it to bytes. More flexible, changes the interface, made the rest of the code look a lot nicer. Anyway, and so that works as far as I know. I've got this helper function which just converts an array of U8 to a 128-bit block. It only works for lists that are 128 bits long, effectively, or less. It doesn't work doesn't generate multiple 128 bit blocks. It could, and then I still have this enumeration that I'll use in the decryption method, which I haven't used yet. And so that's all we've got now. So the code is a lot simpler, and I need to keep fleshing out these tests. This test is disabled because you're still using the 128 bit block interface, and it doesn't make sense anymore. I need to change this to bytes. So that's it. Pretty simple. Nice. I mean, not clean code, but reasonably straightforward code. Apart from maybe the decryption, the encryption method here, it's just a jungle of mess that I'll have to improve at some point. All right. Now, let me just see. Okay. All right, so what I need to do here is implement. I mean, I could go and start building out the test harness, but to be honest, that doesn't excite me too much, and it would be very boring to watch. So what I'm going to do is jump straight to the decryption method. Before I do that, remember I'm putting all this in GitHub, so feel free to go, join me in sort of following along here. This is all landing in the AES-GCM repo. So you'll see all the code here, which is what we've just sort of walked through very quickly. I've been adding quite a bit of stuff on GitHub as I build out more crypto stuff and just other bits and pieces. So my AES implementations here, I've implemented SHA. What have I done? SHA 512 and 256. And I've got a password-based key derivation function, which I'm not going to use, but that was fun to build. And HMAC, so I've got a SHA 512 HMAC SHA 512 function or implementation, which we'll use at some point. And then I'm starting to build a HMAC-based key derivation function as well. And so that's used. You can see I'm starting to work towards TLS, right? So this is my little gist where I've got a whole bunch of things that I want to build over time. And effectively in the crypto list, I'm kind of knocking these down. So I'm almost done with GCM. I've got my SHA 256. I've built these bits. And then once I get to this point, I should have effectively something like this. I should be able to do all the crypto for TLS AES-128 GCM SHA-256. Then what I need to do, so this is gonna be enough to do the I think the record protocol or the encryption for the record protocol. Then what I need to do is for TLS, and then what I need to do is build the handshake protocol or the crypto for the handshake protocol, which means that you need a key derivation function, and you need, as far as I understand it right now, and you need a key exchange algorithm. The key exchange algorithm relies on either RSA or Diffie-Hellman. I've chosen Diffie-Hellman. And for TLS 1.3, I'm going to use an elliptic curve algorithm. The basic one that I'm going to use is the 25519 curve. And so the key exchange algorithm is, based on that, is called X25519. By default, I think Chrome uses that to negotiate TLS connections. And so then once I've got that, I think what I can do is use this key exchange algorithm to establish a shared secret, use the HMAC key derivation function to then build a shared secret key based off a nonce and that shared secret, I believe. And then the nonce is effectively the salt, I think. And anyway, we'll go into that. I've started building that already, actually. But just very, very simple. So there's an extract and expand, and there's a salt and the key material, and it generates the pseudorandom key. You do that first, and then you do an expand. That gives you the output key material of a certain length. And so, that just uses my HMAC SHA-512, which is nice. So it's all starting to come together. And then, but yeah, it's not, I've just sketched out the implementation here. It's actually not anywhere close to complete. But this is going to be a lot. It's going to be quite a simple implementation. And so that gives me, I believe, it gives me the ability to do a shared secret that can be used per session in TLS 1.3. And then that key material goes into our GCM, which is kind of exciting. So we're starting to get, I don't know, like I'm learning this as I go, but it's sort of starting to all come together. The really hard bit though that's left, apart from all the protocol implementation for TLS 1.3, which will be fun in its own right, because it's a whole different type of programming, right? It's not crypto at all. It's just using crypto libraries and implementing the TLS 1.3 spec. The outstanding bit that is going to be non-trivial is the key exchange algorithm based on the 25519 curve. So we're going to do elliptic curve Diffie-Hellman key exchange. That is not straightforward, I don't think. I'm not sure. At least I'm not going to try and do a performant one. I found a really cool presentation from, I think it was RustConf 2017, and the team that built, they're building a whole bunch of crypto libraries under Dalek. That looks amazing, and it's like they're real crypto guys and girls, and they know their stuff properly, and they're implementing it beautifully. They implement AVX support and different backends, U64, U32 backends, and they've built, it's like this middle layer protocol that you can build on top of, and they've also built an X25519 implementation based on that as well. That is very, very cool. And would be super fast and performant and robust and probably very secure. I'm not going to do that probably. I'll just try and build everything from scratch. This is not a production implementation in any way, shape or form. It doesn't pretend to be. This is all about learning. But anyway, it's starting to come together. So yeah, that's the bit, right? Once we've got GCM stuff done and then the HKDF implementation done, that will be the last bit of crypto that's going to break my brain, I think. But it should be fun. And anyway, so enough of me babbling. Let's get back to what we were trying to do, which was start implementing some decryption. And I guess let's have a look. Excuse me. So this is the decryption spec. I haven't looked at it yet, so I'm gonna. Doesn't look a lot different, does it? Ghash, cipher, GCTR, MSB, Ghash. Okay. Yep. So it looks pretty easy. Famous last words looks pretty easy. Probably isn't. All right. So what I'm going to do, let's start with a test case. So we'll need, where's our decrypt bit? We'll do the same thing. We'll use the hex module. Now, we'll use, what are we doing? This is for 192. So we'll use decrypt 128. So that's for AES-128. We want some additional data. So let's do length, I think it was 120 bits, sorry, I think we used, no? AAD length was 128 maybe. Okay, so, and this is with no plain, this is, okay, these things fail. So we have a ciphertext. So this is obviously a test case for the just authenticated data. And it just validates that. So that's the thing with this, with GCM algorithm. You don't need to have any ciphertext. All you might be doing is passing the data in the clear with the cryptographically kind of secure tag that shows that it's that the data hasn't been tampered with. Because remember, that's what GCM gives you. It gives you encryption, and it also gives you integrity checks. But anyway, we want to do something with plain text or ciphertext. Let's find some data, and let's do something with more than one block. Well, I guess we could just start with something like this, couldn't we? I want something that passes and something that fails. So, I guess let's just do this. Let's do both. We'll do... not sure what the counts are. Anyway, let's just maybe take this one. So this is more interesting, right? Because it's giving us... This is an example where things are bigger. Actually, I'll do the bigger one. It's more interesting. And we want one that passes and one that fails. So we've got this. So this is clearly all broken, all just not valid code. Now, let's build a test. So we need to test the passes or fails. Test passes. So we'll do, oh my goodness, do let key, let IV, let CT, let AD, okay. Why is it so slow? All right. So vec from hex. So we'll take that, and we'll basically paste that. Paste that. And we'll do the same thing here. Oh, what am I doing? Could have introduced a subtle bug there, couldn't I? So that sets up our test that fails. And we'll do the same thing for the test that should pass. So I think Rust just lets you shadow variables like this, which typically would be bad code and potentially introduce subtle bugs. But let's see. So we'll need all of this. That's right. And then same thing here. Okay. All right. So now the bit that we care about here is, let's have a think. So we need to call GCM decrypt, and that requires the initialization vector, the ciphertext, the additional data, and the tag, and then the plain text, which would be optional. So I'm not using optional here. I'll allow, empty strings to be passed. But I could use an option type or something, but I won't. Okay. All right, so we'll do IV. We'll do ciphertext. We'll do additional data. And the tag. And then we'll need plain text to be mutable, will we? Yes, and plain text will need to be defined, so call it PT. And so we'll need let PT equal, and we'll just make it a vector of, well, it needs to be mutable. And we'll make it a vector of bytes. There's probably a better way of doing this, whatever. Standard result. Don't need to unwrap, do I? Do. Oh god. All right. So we'll do expect couldn't parse key. We'll do all this again. Couldn't parse IV. Couldn't parse ciphertext. This one was the authentication, the additional data. So we'll do expect couldn't type. Oh my god. Couldn't parse AD. This one would be expect couldn't parse tag. ISV. Couldn't parse tag, and this is plain text. Okay. So we'll need the same thing here. But we don't need test. I we do. All right. And so in this case, well, GCM returns something, doesn't it? What does it return? Returns an enumeration. So we'll just say result. Let result equal that. Type. Now, we expect result. So we need assert result. Is going to be authenticity fail. Is it fail or failure? Partial equals. Okay. Where was it? Fail and pass. Okay. So we'll need to derive partial equal or something. What was it? Can I just do derive partial equal? So much easier. It's wrong, isn't it? Ah, what the? Is it like, how does this work? Is it like this? No. How do you do derive like that? Yeah, it should be that. Using partial equal. Excuse me. Cert equal. What's this problem? Can I do that? Authenticity cannot be formatted using blur. So I need to derive debug as well. I don't know if that, let's see. That may work. So anyway, we'll do this and we'll expect the result to be a failure. So it should, so in other words, you know, it won't be able to pull the, oh, and I don't use key. Because key is implicit and my function signature is wrong. So we'll do key. And then we'll go GCMAD, and we'll add in a key, which will just be another slice of bytes. Okay, that's better. So that's probably enough for the first test. And then the second test we get, we want to assert that the result is a pass. And we also want to make sure that the plain text matches. So we'll assert that the result is a pass. And we'll assert that the test plain text is equal to plain text. Okay. I think that should be enough. Let's just see what happens. Cargo build, cargo test. Awesome. So you get a failure. And that's because we're always passing. Always returning pass. And it fails. Good, good, good. All right, so this is our little miniature test harness for the decryption part. We can get rid of this now. Don't need this, I don't think. Actually, we'll leave it in just to make sure we haven't made any mistakes until we're happy. And then now we can go and implement this decryption bit. Very cool. All right, so what I'll do is I'll just take a quick break just for 60 seconds or 2 minutes or something, and I'll be back, but we'll come back and we'll do the decryption part. All right, we're back. So what I wanted to do, I don't think it'll take too long, but we'll see, because the thing with doing these kind of algorithms, like I saw this when I was building AES, was building all the helper functions and all the associated machinery to do the encryption or the cipher was the hardest part, and then the decryption is usually, or the inverse cipher, or in this case the decryption, is usually pretty straightforward because you've kind of tested everything and you've got a good idea of what's required. I believe, so this, so what's interesting is the decryption with GCM never calls the inverse cipher for AES. It just uses AES again, I think. So anyway, we'll look into that. We'll know that after the implementation, won't we? So all right, if we have a look here, we've got our GCM AD, key IV, ciphertext, data, tag, and then we're going to put plain text in there. We may need a tag length again, maybe not. Probably not, because the tag is already the right length. So we've got a cipher, we've got a key. But we'll need to do the same kind of thing. We'll need to build, yeah, anyway, we'll get into that. Input is IV and ciphertext, A and T. Output is plain text or indication of fail. Yeah. We'll always return a pass or a fail. And if it's a pass, then we'll know that plain text will be there, or I mean, it will be an empty string or something. Okay. All right. All right. Okay. So anyway, let's get started. So, we'll look at the spec properly this time. So if all right, starting step one, if the bit lengths of IV, A, or C are not supported, or if the length of T does not equal T, okay, so we will need a T. We'll need a tag length. Excuse me, we'll call it tag size again. It'll be U32, or U size. Actually, what did I do it last? I can't remember what I did last time. U32. It's probably U32 is way overkill, but whatever. U size is probably more appropriate though. How was it used? Tag size. Yeah. Then I guess yeah. What is the tag size here? It's 16 bytes, 128 bits. So we'll do 128. Okay. All right, so we'll do that. We've got a tag size. And so we need some kind of checking for what's supported, don't we? So to do, check that IV, A, and C are of supported bit lengths. But then we'll do the if tag length doesn't equal T, then return authenticity fail. Tag size even. All right, so we've got our first little check in there, but it's not complete. And then we need to build the hash subkey again. So we need to do the same thing as last time. Which is basically this bit. So function get hash subkey, where we pass in the key. And we get back a block. Okay. So let hash subkey equal get hash subkey with key. So we'll do the same thing here. Right. So we build the hash subkey. That gives us the block that we need, and then we define as J0 block. So it's exactly the same, is it? Looks like it. Get initial init counter block. All right. Still need key schedule. So it needs to return, needs to build a key schedule. What else do I need? Just that, I think. So we need a key schedule. The U32. Hash sub key. Let's see. Bar is mutable. Okay. All right, so if we go back to what we're actually building here, I'm just sort of pulling out some of this stuff into helper routines. We'll need to do the same thing probably for function, let's say init IV or something. But it'll be a padded IV, won't it? And so I think all we need is IV bytes, I think. IV bytes, which will be immutable. Oh no, it won't be mutable, will it? It'll just be a reference to bytes, I think. And then, but we will need a init IV, which will need to be mutable. And then it'll be something like something like this. J0 block. Oh yeah. Oh yeah, we don't need padded anywhere else, do we? We just use the IV, I think. So I think we should just be able to do something like, don't quote me, but something like this. I think. Where we just take I think we do let J0 equal init IV, and we pass in the padded IV. So I think it should just be something like this, I think. Okay. I don't know. What does padded IV need? What do we need? We use. We just G-hash it. Yeah, so I don't think we need this. Well, we just need to pass in, I believe, IV bytes like I originally thought. Something like this with the hash subkey. No, hash subkey should be U128. So hash subkey U128. This doesn't need to be mutable. That should return the right thing for us. I believe. Play some music while I'm trying to work. All right. So it looks very much the same. I mean, it's almost like we're just re-implementing this thing. So I think that's the same implementation. IV length S128 rounded up. Yeah, it's the same. So IV is the same. So I think we can share that without any problems. Just cleans up our code a bit, which is good. Okay. Mutability. So it's when we get down to GCTR that things change. So this was, or does it? So this increments J0 and passes plain text, and we get a cipher out of it. Obviously, this is symmetric. WTF. Okay. So we don't need ciphertext. So in this case, what we're doing is we're just replacing ciphertext with plain text. Plain text needs to be immutable. Dun, dun, dun. So plain text needs to be a vec. Vec of U8. Let's be mutable. Of course it does. So this does exactly the same thing, but we pass in ciphertext. So the ciphertext is the bit string we pass in, and plaintext is the output. Head's starting to explode, but that's okay. I think I get it, sort of. And then all this other stuff stays the same, I think. And so we basically build the same tag. And then we just check whether or not the tags match. And if they do, then we return the text. So I'm going to have a different interface there, but that's fine. And so all this stuff stays the same. All right, so we just do we don't even do this, right? Well, maybe we do. Let tag equal equals, okay, and then I guess we need to pass everything in, don't we? We need to pass the data. Hang on. Additional data needs to be passed, clearly. Okay. Anyway, so additional data, the ciphertext. What else needs to be passed in? The hash subkey. Ciphertext. The hash subkey. Key schedule. Key schedule. J0. And that's about it, I think. Tag size. I think that's it. So let's build a function called tag. Can we call it build tag or something? Build tag. Alright, so it doesn't return anything. What it needs is needs additional data. It needs the ciphertext. Cipher text, which should just be, well, it's going to be mutable. It doesn't need to be. Whatever. Needs the hash subkey. Subkey needs the key schedule, which is going to be a just a reference to, well, what's key schedule here? Needs J0, 128, and it needs tag size, which is going to be use size, something like that anyway. And then pretty sure we just lift this. Pretty sure. quite. We need tag. So tag needs to be reference to vec u8. It's already borrowed. I wonder if it needs to really be that accurate. All right, and then tag needs to come in here. Hang on a sec, make sure. Tag size. Which one goes first? Is there a convention? Yep, tag. Wow. This looks more interesting, doesn't it? Let's see what happens. So does this still pass my... Yep, that still works. Wow, cool. So we need to do the same thing for our decryption effort, don't we? So it's literally going to be this decryption. So we build the tag. Yeah, but we don't need mutable. That's the problem, isn't it? Tag doesn't need to be mutable. So this is getting ugly now. I'll do this, but that's not gonna. Okay, so tag also needs to be a vec. And then you change mutability down here, which is just sucky. Doesn't need to be. So this is where the interfaces don't quite line up. Same as this. Yeah, I don't know. I'll probably refactor this because it's not obvious why these things need to be mutable when you're doing the decryption, because they don't need to be. It's a bit of a pain. Encryption still works. But anyway, pragmatism, right? and in fact, the weird thing is, it looks like the implementation is identical for most of this. And then we still get tag. I think. Returns fail. So we still get the same thing. And then we just check it. We say if tag, if the computer tag is the same as so let computer tag equal well, it needs to be mutable. Let computer tag equal it's a vector. Yeah, this is bad. Anyway, we'll do it this way for now. So we'll make it this new vector of bytes, and then we'll say it's computed. It's going to be a mutable borrow of computer tag. And then we'll say if tag's the same as computer tag, then we can return authenticity pass, else return fail. Computed tag equals computed tag. All right. Ah, my goodness. What's wrong with my typing? Computed. What's going with my computer? Why is everything so slow? Okay, I can't do equality. Better do a match. Okay. If it's equal, then return P, else return fail. Okay. So I think that's kind of a first pass. But obviously we're failing somewhere. Excuse me. 465. We're failing here. So we're not getting a pass. Do this. There you go. Plain text isn't getting populated. It's because I don't actually put it in the byte, so I never populate plain text. plain text. Oh no, should be. So this isn't working. Ciphertext is passed in. So I'm expecting it's 85 in hex. On 3.3. Okay. So who knows why that could be failing for lots of reasons. So the key schedule isn't, oh, sorry, the plain text isn't getting built. Output to plain text. Plain text was passed in here. The encryption still works. Why don't we get anything back? It's so weird. Why aren't we getting any debugging? So I guess let's do print line J0. When in doubt, start printing stuff. Tag length. Times 8. That would help, wouldn't it? Yeah. Let's try this then. What's tag length? Tag size. Tag size. And tag length. Tag length times 8. Tag length. Oh, okay. So I can't count. Tag was 24, 12 times 8, 96. Right. So this is 96, not 128 bits. I mean, I could just do I could just do tag.length here, but whatever. Let's see what happens now. Passes. Wow. That's always concerning when things pass that well. Cool. That looks awesome. So we're now getting a pass. I'm going to take a small break and reflect on how easy that was. And I'll be back in a minute. All right, so so we actually got that working a lot faster than I expected. And isn't that interesting, right? Excuse me while I eat some chips here. We've kind of refactored the code, so it looks a lot nicer. Right, it's much easier to read these things now. Right, we build a schedule, we get the key, we initialize the, we pad it in the IV, and then we build the ciphertext and build the tag. In this case, if the tag length isn't right, we fail immediately, which is what was happening because we were computing that incorrectly. Then we build the key schedule again, and hit the IV and build the ciphertext. No, we build the plain text. And then we don't need to print this anymore. And then we build the tag again, or compute the tag. And check whether or not the computed tag is the same as the tag that we expected. All right. And so in a way, my interface is a bit different, right? So I could do things like, you know, if authenticity passed, then get the plain text. But anyway, and so we're sort of done. Obviously, build tag is pretty ugly. And the interface is all wrong. The mutability is wrong. Gonna have to think about that. Anyway, I won't eat while I'm on video because it's really annoying. Bad enough that I'm slurping tea. Yeah. Well, anyway, we don't need all this stuff in mol blocks anymore. In fact, we don't even need this debugging output. I've really confused my IDE. Let me just close this thing down. I don't know what it's doing. Whoa. Okay. Maybe it did an update or something. It was really slow, wasn't it? When I was... Anyway. It's still lagging. So I think we're pretty good on the decryption and the encryption for now. Just obviously we'll find heaps of bugs. We'll do more tests. I'm not running tests here for any of this stuff. And so rather than pretend that I'm running them and passing, I'll do ignore test for these. How do I do that? Rust ignore test. Ignore. That's helpful. Oh, ignore, cool. So I'll do, is it just ignore? Yes. And I'll do the same. I'll do the same for the unimplemented tests, I guess. Oh, but then it'll still throw errors. Anyway, okay. So we don't run these, we don't have tests for them. And we probably should have unit tests for these things. Maybe not. I don't know. It was a little bit hard to debug these intermediate functions. Like I had to, when I was doing the encryption part, I had to find a set of things that, like there are there are sort of other unit tests out there or test vectors and output, expected output with intermediate steps. And so I had to go and find that and sort of use that extra information to debug, because these test vectors I have just kind of give you the, the expected output with none of the intermediate steps. And when you're debugging something that's reasonably complex, right? There's moving parts and all the bit shifting and bit fiddling and all the other bits. You want to be able to go deeper, and intermediate results help you understand, sort of bisect the path where it's failing, the code path. Anyway, so this isn't going to work because it still fails. It won't compile because all this is wrong. Do I want to fix this? Not really. No, I don't want to fix it. I'm too lazy. I will fix that at some point. Okay. So it's ignoring. Okay. So anyway, that's pretty cool. So I reckon we might just push that. What have I done? Git diff. So obviously that test, the implementation itself, refactoring the encryption bit, and then building these other separate functions. Cool. So git add source main, and then we can just say implemented authenticated decryption and refactor encryption. Cool. So I had it here, didn't I? So 21 commits. So this is our commit. It's a good one. Okay. Anyway. So we didn't add a lot of code. I mean, I guess we sort of did, but like if you look at actual lines of code, 381, but a lot of that is tests. So like we've really only got 347, probably like, I don't know, 280 lines of code or something. It's nice. Obviously it's not a, yeah, it's nice. Cool. So that's kind of AES. That's the first pass of GCM done. And then what I'm going to do, I'll probably do this offline, I might share it afterwards, is I will go and build a test harness that knows how to go and parse these like test vectors, or whatever you want to call it. And I'll do that for decrypt and encrypt for 128. And that'll give us a crap load of tests, which should make the code quite robust. Like if we pass all that, I think we'll be okay. We'll sort of assume that things are okay. And then I think that's kind of GCM done for now. I'm not going to refactor it and make it beautiful. I'm not going to try and change the interfaces or anything, even though I should. It's really procedural and quite ugly right now, but that's okay. I'll turn it into a library as well. I'll probably turn it into a library, then build the test harness, and I think the only methods, sorry, the only functions that'll be public, I think, will be AD and AE. I think. Yeah. Oh, and then the enum, I guess. Yep. Yeah, and that will be it. Cool. So, so that's pretty much done. Which is kind of cool. And isn't it interesting? It's because of the hash, isn't it? We just need to apply this exactly the same method. Plain text encrypt and ciphertext flipped. Yeah. Very cool. So that was a lot of fun. This one took me a long time for some reason to build, and I think it's just because, I mean, it's pretty involved, isn't it? From the perspective of what the flow of the code. It was AES took me a long time to build too, though, to be fair. Yeah. Anyway, so that's great. And then I guess, if you want to watch more crypto stuff, I'll keep probably live streaming it. I don't think I'll turn into a set of videos because I don't know, I'm not that organized, and it's also quite involved. It's taking quite a bit of time to write this code. Like I spent a couple of hours on it over the weekend, for example. The last few days, sorry. Anyway, and so that'll do it. I think we're done. Feel free to jump in and sort of look at the code. I mentioned it's all in GitHub, so feel free to jump around and have a look at that. Follow it. Give me, pull requests. Tell me about how bad it is. And I'm gonna probably upload this to YouTube, so feel free to sort of comment below and tell me what you think about it. It's really scrappy, obviously. This is not like a nicely curated video where I've sort of prepared and thought about it ahead of time. It's just as I do it, as I think, as I learn. But like it if you liked it. Be constructive in the comments and follow me if you want to see more of this stuff. I just generally am putting Rust programming, live coding, and or more curated Rust programming videos on my channel at the moment. So it's all sort of Rust specific at the moment with for different use cases. And then in the future, what I'll do is I'll probably put more of these. I'll probably build the HKDF thing offline pretty quickly, and then maybe the next one will be looking at the elliptic curve crypto work, which will be the last part of the puzzle, I think. As I mentioned earlier, the key exchange algorithm will use that. All right, so thanks everyone. Hope you enjoyed that, and don't forget to subscribe if you want to see more of this stuff, and enjoy writing some Rust. Go and do it. It's heaps of fun. See ya.